So in today's talk, we'll be talking about using Intel Sapphire Rapids and how we use hardware accelerators within that. Sapphire Rapids is the latest processor in Intel's offerings. My name is Akash. I am a tech lead and a software architect at Intel, and my team works on OpenSearch and various optimizations. Today, I will also have a partner speaker as part of my presentation, Michelle Tabirao from Canonical. The things that I will cover in today's talk would be around hardware acceleration with OpenSearch. I will touch upon two specific use cases. One is for vector search using AVX512. The other one would be around compression, which uses another accelerator called QAT. I will also touch upon a partnership through another foundation called OPIA. And then finally, we'll also go over the collaboration with Canonical. So to just set context for this problem, a couple of challenges which were very evident through all the presentations today in the conference. There is a clear trend of a growth in data. I mean, last year we were talking terabytes. This year it's petabytes. Maybe the trend will go on. Who knows? So that shows a clear need for compression. I mean, if you can compress your data, hey, why not save on storage? The other trend which is also evident is how quickly vector capabilities exploded. The need for vector search, semantic search, RAG, a lot of use cases started getting built. And those present interesting challenges in their own ways. And with regards to why hardware acceleration, a couple of themes that we see playing out in the industry are like the hardware innovations that are happening today. They will drive the data management systems of the future. Then, in addition to that, this also opens up doors for hardware-software co-design opportunities. Also, another interesting trend that's playing out here is the disaggregation between compute, storage, and eventually main memory as well. So some of these themes you will see in various presentations, talks, in the conference, in the industry, and that motivate this presentation for hardware acceleration as well. Before we get to hardware acceleration, just a little bit of context. So people know Intel as a CPU manufacturer and maker of processors. Another hidden fact about Intel, which is not well known, is the contributions Intel makes to open source in general, including OpenSearch. Intel has a long history of contributing to various technologies, Linux kernel, PyTorch, and now OpenSearch. We also made some contributions to Postgres this year. So in OpenSearch, we contributed the Z-standard compression feature. Following that, we did some tuning guides. Then earlier this year, we contributed code for QAT-based compression. And more recently, as of this month, actually, we upstreamed some changes for AVX512 for vector search. Now, going back to the topic of hardware acceleration from that slide detour, why do we feel the need for hardware acceleration? A couple of themes come in mind. Performance. Yeah, if you have hardware, dedicated hardware, you're going to make things run faster, improve your system performance. Hardware acceleration can also bring energy efficiency to the system, meaning there's a bigger theme of the providers who manage data centers that they want to make it more efficient, like lower their carbon footprint. So accelerators play a part in that. And finally, it helps you make better use of your compute. And the more better and smarter you get about your compute utilization by offloading heavy computation to dedicated hardware, the more efficient your application becomes at the end. These are great themes, but is this enough motivation to start exploring the problem for OpenSearch? Let's see. So we started in the more traditional way. We ran a benchmark What you see on screen is a standard vector search. I believe this is a Cohere dataset using OpenSearch benchmarks. This was using Lucene as the vector search library. And within Lucene, we did a profile. So for the folks who are not familiar with what you're seeing, this is a flame graph. It breaks down your application into how much time is spent on each method in the code. So the two things emerge here. In pink, I did a search before this. So in pink, we have the methods that were taking time for compression, which accounted for about 10%. And then blue is your vector search, so the time spent on actually doing vector search. That includes building HNSW graph in this case and other things necessary. So on a holistic picture, if you look at both of these together, it's taken about 50% of the time, which is huge for any application. Now, if you take a step back and see that if you can optimize 50% of your application, that's significant. If that 50% can be brought down to a much smaller number, hey, you've achieved significant strides in your application performance. So let's see what happens from here. So from here, I will pivot onto results and explain some of the things that happened when we did hardware acceleration using these accelerators. So fundamentally, before we get into results, let's understand where is this happening. When we talk about accelerators, let's break this OpenSearch architecture a little bit. So at the very top level, you have a core OpenSearch, which has a KNN plugin. KNN today supports 3 different libraries, Lucene, Faiss, and NMSlib. I think earlier presentations also touched upon these. And each of them will their own index. So ultimately, this index, which could be HNSW, which could be other techniques, they all need to run on some compute. At the end of the day, they are doing very intense computations. They're doing math, which is a dot product or an inner product. That's what's happening. And that intense computation is the hotspot you saw in the flame graph. That's where the bulk of your time is getting spent. The other side, the arrow which goes straight to Lucene, is the non-vector component, where you don't really need a KNN index. So that hotspot is what gets accelerated when we introduce an accelerator. Now, how do we use these accelerators in an application? There's a couple of ways for like Faiss and NMSlib, which are native libraries, meaning written in C++. There is intrinsics. Intel offers intrinsics, so you can use intrinsic code, which will allow you to actually call and use AVX512 registers. Lucene, on the other hand, which is Java, makes use of the JDK vector API, which is available as a package. And using that package, you can achieve the same amount of speed up that you would see on the intrinsic side. So fundamentally, they use SIMD libraries, and that's what is happening under the covers to provide that speed up. So let's look at some results of what this actually does. This was our setup. So we used Cohere as the data set, 768 dimensions, 10 million documents. JDK version was 21, and the engine of choice here was Lucene. On the right-hand side, you can see some of the configurations that were used for the graph construction. Nothing special about it. And this is the results. Let me pause here and try to explain what's happening here. So the vertical lines you see represent 3 different products going old, new to newest for Intel. So R5 is what we understand, as far as we know, the majority of the customers use today. And as you go into new hardware, you can see significant improvements. I tried to break it down by just between R5 and R6 and R6 and R7i. 7i is the latest Intel family. So looking at it as the holistic picture, you can achieve about a 43% TCO going from an R5 machine to R7i, which is Sapphire Rapids today. It's significant. It's significant to just not do anything, just change your underlying hardware and achieve that gain. Now, so far in this calculation and numbers you're seeing, there's no vectorization or no AVX512. This is just pure machine hardware. Let's take this to the next level and see what happens when we actually use AVX512. So this slide covers AVX512 and what AVX alone will add to as the value proposition. So the top graph is for indexing. So when you measure pure indexing performance and how it changes. And then the bottom one is for search. We saw more improvements in search in this particular benchmark. Others have reported better on indexing, and I believe it's very workload dependent. Just purely adding AVX512, you can see about a 31 to 35% improvement just as a result of vectorization. So even with no machine change, keep the same machines, just turn on this capability, you can get that much improvement in a vector search benchmark. Now, I'm not going to calculate this for you, but if you add those two together, if you have a machine, older machine, no vectorization, to the latest with AVX512 turned on, you pretty much are stacking those gains, like the 43% you saw previously with this 35% up here. So that's close to a 70-75% improvement, just from partly due to hardware acceleration and partly from new hardware. So that's the value proposition that hardware alone will bring to you. Also to note that the cost between these machines, mainly on Amazon, we only measured on AWS, is not significant. Going from R5 to R7i, the price goes up by 5%. So for a 5% increase in price, close to 60-70% in performance, it's worth considering. Okay, so I will take a pause here and switch to QAT. And okay. So that was about vector search and AVX512, and then from there I want to pivot towards the other accelerator, which is called Intel Quick Assist technology, also known as QAT. So where can you find this? Firstly, Sapphire Rapids and newer. I think different clouds call it different terminologies. And I have a slide at the end which will show you by what name you can find it in your clouds. Intel brands it as the 4th gen Intel scalable processor. Now, what does it do? It's used for encryption and compression. So compress, decompress, encrypt, de-encrypt. These are, if these operations are happening in your workload and profile, they could be offloaded to this accelerator. Now, if you take this computationally intensive portion, like when we saw the 10% previously, if you take that 10% away from your CPU, put it on an accelerator, and let the CPU do other things, it gives you two benefits. One is that dedicated chip, which is brought in for compression, will do it faster. The second part of it is your CPU becomes free to do other things. So it's a twofold benefit. And finally, the bigger benefit to an operator is data center efficiency, which is power reduction. And the right-hand side, there is a small diagram up there, which kind of shows where these accelerators are found. They are part of the die. So when Intel manufactures it, it's not like an off-board device. It's on the die itself. So the distance between the core to the actual hardware is very, very small. Generally, when your distance increases between two components, your performance suffers. But in this case, you can see it's right next to the core as well. A more important part to note is the algorithms it supports, deflate, LZ4, and Z standard. On Z standard, we support, currently it supports compression. Decompression is not supported. That will get added in future products. On AWS, it is available on the C7i, M7i, and R7is. And Also, another good news is that this change recently made it to OpenSearch. It is available as a custom codex. It's available in the custom codex repo. So what that means is for any user, they can pick a machine, one of the ones that I listed down here. They can get the codec, enable it, and start seeing the benefits of QAT. This is a slide I presented last year. I took the same slide to highlight what's happening in the stack. So you have, at the very high level, you have OpenSearch. Then you have the compression plugin. As you see, last year it was in progress. Now the work is completed. That calls into QAT Java, which further calls into the driver layers, and then ultimately the QAT engine, which is the hardware component you saw. Pretty straightforward, nothing fancy happening here. And now on to results and what we did here. So the benchmark setup was slightly different from how we did vector search. For this purposes, we went with the Stack Overflow corpus, which is available in OpenSearch benchmarking. And with that, we measured indexing, compression. So we had a single node, meaning we took one of the Sapphire Rapids M7i machine. And then within that machine, that has 192 cores within it. So in that machine, we provisioned 4 data nodes and on a single socket. And the benchmark, which is the client, was on the other socket. And the results that we saw on the top table compares best compression with QAT deflate. On that, we saw improvements pretty much across the board. Throughput improved by close to 24%. Time improved by about 11%. Storage size that took a slight penalty. It went up by 2.5%. And CPU had a 5% improvement as well. This means, what that ultimately means is you can do more with the CPU. Your storage is slightly worse, not terrible. Your throughput went up significantly by doing this. With LZ4, similar comparison, time roughly the same, 2% improvement. Throughput about 3%. The size came down more, about 12.5%. And then CPU got free about 7%. Now, when we do performance analysis with the data collected on this, the main driver for this type of improvement we see is path length reduction. Path length is for folks who are not familiar with path length, this is the amount of number of instructions that are spent to perform a given task being benchmark in this case. So to run a benchmark, if the CPU took, hypothetically saying, 20 million instructions, with the QAT driver, it would take much lesser number of instructions. So that would lead to this. That would translate into improvements in these metrics. Now, onto the public clouds, where you could actually use these capabilities. So on AWS, we have M7i, C7i, R7i. I listed I4i, but that's one exception. I don't think that has the accelerator. That doesn't have QAT. It has AVX. It's very good for storage, like the workloads that need heavy storage. It has NVMe disks attached to it. So it's a pretty good offering for that category. In Azure, you have some instances, and same in GCP. The public branding for the hardware that has these accelerators is Sapphire Rapids and more recently Emerald Rapids, so from the Rapids family. Next, I will just take a slight pivot to Opia, which is an open platform for enterprise AI. This is about partnerships, essentially, like what Intel has been doing here. So what is Opia? I mean, if we break down Opia in terms of a framework for building Gen AI solutions, like there are lots of building blocks used in such a framework. There's vector databases, there's LLMs, prompt engines. And with these building blocks, you could come up with a blueprint, which is an idea of how you want an end-to-end pipeline to look like. RAG would have a pipeline, similarly, agent systems, AI avatars, all of them have different blueprints. And then finally, you want to evaluate whether the blueprint, the technologies you used, the blueprint you used, achieve your needs. Do they give you the level of confidence? Is it enterprise ready for you or not? That's what fundamentally OPIA is. And Intel has been partnering with many firms in this space who work on the various technologies, vector databases, LLMs, you name them. So these are just some of the values that OPIA has. Like they want to make an open reference architecture, which is efficient, seamless, ubiquitous, trusted, and scalable. At the same time, we want to keep it open so it can continue the theme of innovation that open source brings. So when you have architectures that are open, shared, you could essentially plug and play the components you want. You could swap your hardware. You could use CPUs instead of GPUs. You could use GPUs from one provider. Same time, you can change your vector databases. Same time, you could change your LLM models. So all of these fundamental moving blocks, they can be replaced, swapped based on your needs in such an open blueprint. And I think Intel believes that collaborating in the open is the best way for innovation. So that's what led to the formation of OPIA. And it's not just Intel over here. This is a consortium of many companies. Some of you who are in this room are in the conference, and your corporations are already part of it. So this is a collective initiative in the industry to drive open source innovation. And with this, I would like to call on stage Michelle from Canonical to talk about some of our partner collaborations.
Hello. Thank you so much, Akash, for inviting us, Canonical, so that we can share to you the amazing work we've been doing together with Intel. So if you don't know, Canonical is the publisher of Ubuntu. We are a Linux distribution, but at the same time, we wanted free and open source software to be accessible to as many users as possible. And I think that's why we started Ubuntu, and we're 20 years now and thriving in this ecosystem. Well, in terms of our partnership with Intel, we wanted to ensure at Canonical or in Ubuntu that Intel hardware platform or any features are enabled to have a better compute and performance once you actually run it in an Ubuntu ecosystem. So this is the collaboration that we have. So it's not just about Ubuntu, actually. It's also about the software that runs in Ubuntu. We have a lot of open source software. In fact, 30,000 software packages that is in the Ubuntu archive, or like the universe repository. But on top of that, we make a lot of innovations to make sure OpenSearch, for example, runs in Ubuntu seamlessly. And that's the reason why we actually started different types of projects and artifacts in OpenSearch, such as a snap, so you can run it in Ubuntu in any other Linux environment, or Rock for a container as a container artifact. And then lastly, the operator, which is actually our solution so that you can run OpenSearch in different clouds, both private and public cloud. And we implemented a lot of automations to make sure that anyone wanted to use OpenSearch in different clouds will have your back covered because of those automations. So that's what we call Charmed OpenSearch, and we actually had a GA of that just today. So that's our announcement a while ago. So what do we do with OpenSearch/Charmed OpenSearch, enabling Intel accelerators? So we do have AVX enablement, we do have QAT enablement, and we also cover the AMX part, which Akash already shared. And I'll give you a couple of benchmark results that we have at Canonical. But on top of that, it's also one of the topics about confidential AI on how you make sure that the data and confidentiality of both your model and data that runs in any data and AI applications are protected, secured, and the confidentiality is taken care of. And another one that we're working with Intel is what the trusted execution environment that they're doing, where we make sure that the hardware that we run is confidential with the Intel TDX, and there's a lot of work happening right now, which OpenSearch is one of our core technology. In fact, one of the use cases that I wanted to highlight is, of course, the AVX, where it's a very good hardware accelerator for different use cases. We have tried it. We have deployed it in AWS. We have deployed it in Azure with AVX enabled. And we do agree that running it in this accelerator does make so much difference in terms of throughput and latency, both for bulk index and also the search capabilities itself. You can check it out on the Data and AI Masters coming on October 1st. In terms of the AVX 512, feel free to download or scan the QR code. What we have seen is, this is a comparison of Intel machine, AVX, and non-AVX. So when we use an AVX 512 enabled device, VM, sorry, we saw that bulk indexing, for example, has increased in 34%, and at the same time, and the search part has increased in 18%. And in terms of latency reduction, we have reduced it to 35% for bulk indexing and then 20% for search. I just wanted to just quickly highlight, because in fact, Akash also did it to the upstream, just to also clarify on this side, on the charmed OpenSearch, which is the operator. We make it as a first-class citizen in terms of security as well. So automatically, when we set up it, we look at it in a production environment. So there's a TLS enablement that causes a little bit of, not so much of the grade, but in comparison to the upstream, a little bit of a difference on the search part, on the outcome for both the throughput and the latency reduction. So that's the use case that we have, and I can't wait to share you more with other use cases that we're working together with Intel.
Thank you, Michelle. Well, that's a really good improvement, I think. So with that, let's move on to what else is going on in this space and what we are planning to do next as a company. So on the front of vectorization, if we bucket these problems in various areas, like vectorization itself has several opportunities. We've been looking at the Faiss library in particular. There's several opportunities over there to improve via vectorization and using AVX. Quantization is another aspect where the techniques such as FP16 and byte quantized vectors, they are all good candidates for vectorization. As a matter of fact, we made some changes in a related ecosystem, PG Vector, where we saw good improvements on byte quantized vectors, specifically which use Hamming distances and Jacquard distances. Those are the techniques used for computation, and they use an underlying method called pop count, or population count, and that's a good candidate for vectorizing. Using AVX 512, and more specifically within AVX 512, there's an FP16 implementation as well. Finally, we also want to integrate compression acceleration with vector search. There's some challenges we have to work through to load the compression plugin or codec and the KNN plugin. So that is still something we want to address. And lastly, I also wanted to put it out there, AVX 10, I believe the spec has been shared by Intel. You're more than welcome to check it out. That will be the next advancement on the AVX technology front. It's not there on any public product as far as I know, but it will be coming out very soon. The spec is there for everyone to take a look. With this, I would like to thank the following people, left-hand side as part of Intel and on the right side from the community, for your help in various forms, getting the changes, discussion, brainstorming ideas. And you have my email. You also have my GitHub. And feel free to reach out with any questions in either of those channels. And finally, I'll open it up for any questions.